structures, structural health monitoring, biomechanics, and engineer bamboo structures. Dr. Bhalla has been very active on R&D collaboration with several UK universities such as Dundee and Bath, and hopefully Huddersfield. Dr. Bhalla is the founder of Smart Structural and Dynamic Laboratory at Indian Institute of Technology, Delhi. Dr. Bhalla?
Thank you, ma'am. So, good morning, all ladies and gentlemen. So here I would be presenting the fatigue life assessment of structures using electromechanical impedance technique. And the paper which I am presenting here is actually sort of a review of my own over a dozen papers. So here I would begin with a brief introduction to the how piezo sensors work for structural health monitoring and how mechanical impedance approach this can give us a better index for damage assessment, and then coming to fatigue life assessment, and then some new developments. So basically here I will provide a glimpse of the recent outcomes of our laboratory, and it's essentially based on my own review papers. Now, civil engineering structures, they have a lot of vulnerability to fatigue damage, because fatigue is a slow and process which takes on in the background, and the fluctuating stresses, they are responsible for that, and sometimes when we realize, it's too late for us. And the civil engineering structures like bridges, most of them, they are determinate structures. So they are especially vulnerable to this kind of damage. Say for example the Samsu Bridge in Seoul. So it failed because of the failure of one member that resulted from the failure of the welded connections. And being a determinate structure, so it had a devastating effect. And in fact, Acton has written a paper where he has pointed out a lot of such vulnerable components in our bridges, which are sort of very critical, and if any failure occurs in those members, those components, then that has a detrimental effect on the health of the structure. So the main structural components, they may be still intact, but because of the failure of such components such as hanger pin, the entire structure, it comes down. That's why the importance of structural health monitoring is now highlighted, and it is defined as the measurement of the operating and loading environment and critical responses of structure, so as to evaluate and possibly in a preemptive manner any anomalies and any deterioration which might affect the operation and the serviceability and safety of the structure. And put in other words, basically structural health monitoring system, it denotes a reliable system which has the ability to detect and interpret any adverse changes in the structure. So the reasons of structural health monitoring, they are very obvious. We want to detect such effects like damage in a timely manner. We also want to do design validation, especially in civil engineering structures. We have a lot of uncertainty when we do design. Our designs are different from the mechanical engineering designs, which are more precise. So we have great difference from the actual design parameters used in calculations and what we get in the field. And if we have an old structure which has been retrofitted, then we must have some quantification, and in very reliable terms, we should be able to sort of confirm that the retrofitting has been successful. So here also monitoring comes into picture, and of course the conventional approach of visual inspection is not possible. It's both practically and also from the point of view of the cost effectiveness. It's not something which we can rely upon. And if we have a structural health monitoring system, we can have have a lot of data and a lot of parameters through which we can monitor these structures. Now, unfortunately, in civil engineering structures, this is not the case. The civil engineering industry is still not realize the full potential of the structural health monitoring. On the other hand, if you buy a car which costs much less, but it has a lot of sensors, lot of parameters being monitored in real-time manner. Now I will cover basically the structural health monitoring for particular instrument using piezo sensors, and here I am relying on the electromechanical impedance technique. So I will introduce this technique first, and piezoelectric materials. So piezo materials, they are smart materials. They show two effects. The first is the direct effect, that is, if we apply a stress, it leads to the development of charges. And conversely, if we apply an electric field, then that leads to the strain field. So whereas the direct effect is used in sensing applications, the converse effect is used in actuator applications. So commercial piezo materials, they are available in ceramics and also as polymers. Ceramics, they are high on strength and stiffness but brittle, but overall the ceramics, they have found more acceptability in the industry, and they are in fact suitable both as sensors and actuators, whereas the polymers, they are more suitable as sensors. So there is one more thing. We use the direct effect as sensor, converse effect as actuator, but we have something both direct and converse effects together, which we call as the electromechanical impedance technique, or the EMI technique. Now, it is sort of an interface between the global vibration techniques and the local non-destructive evaluation techniques such as the ultrasonics, because its principle is similar to the global vibration techniques. However, it implies frequencies in the high kilohertz range, and because of this effect, the sensitivity is typically as high as the local ultrasonic techniques. And the key sensor for the EMI technique is the piezoelectric sensor. So typically this is a model of the piezo sensor bonded to a structure. So the structure is represented as a impedance element, and this is how the piezo is vibrating when we apply an electric field. It interacts with the structure. So here we have the first the actuation effect. We apply externally some electric field which actuates the piezo into vibrations. It then interacts mechanically with the structure, and the response in terms of the current flowing through the circuit, that is sort of captures the essence of the structure. So this equation basically defines the relation between the electromechanical admittance, that is electrical parameter, and the mechanical impedance of the structure. So mechanical impedance is a parameter, so physical in terms it's related to stiffness, mass and damping, and this equation basically relates the structural parameter to the electrical parameter. So measuring directly the mechanical impedance is very difficult, and especially if we want to measure at high frequencies, this is impossible. On the other hand, using the EMI technique, we can very easily obtain the electrical impedance, and then we can derive the mechanical impedance through this equation. So this serves to provide an indirect measurement of the mechanical impedance of the structure. So if there is any damage in the structure that leads to the changes in the stiffness, mass and damping distributions, that is a change in the mechanical impedance, and that serves to change the electrical admittance of the piezo patch, and that provides us an indication of the damage. And put in other words, we can also visualize through the wave propagation phenomena that we have the piezo which emits surface waves around, and if there is any damage, then that damage disrupts this path, and because of this disruption, the overall dynamics of the system changes, and that leads to change in the electrical admittance. So here there are two implications. One, that because of the small wavelength, because frequency is high, so naturally the wavelength will be small. So the it's a very local area that comes into the picture, and here the local structural modes are excited. This is one implication, and the second implication is that the sensitivity is very high. The sensitivity is high because we are using high frequencies and small wavelength. So small wavelength is very sensitive to any incipient damage. So this helps us, though this someone may say that this is a disadvantage, that the sensing area is small, but this helps us in localizing damage. So the key equipment for the measurement is the LCR meter. So this is one typical commercially available product, and basically the electrical impedance, which consists of the real and imaginary part, and if we invert it, we get the admittance. So typically in the EMI technique, it has been now the norm that we don't measure the impedance, but we measure the admittance, which consists of the real and imaginary parts, the conductance and susceptance. And this is showing a typical plot, the real and imaginary plots of piezo patch bonded to a steel structure, a steel beam. And here typically a small damage has been done by drilling a small hole, which constitutes a very small insignificant mass loss. And now this is the signature in the undamaged the pristine state, and after drilling the hole, the signature changes appreciably. So this provides us the indication of the damage, and this can typically capture very incipient damage. Now the question which comes to mind is how to quantify this kind of damage, because this is a signature based approach, and signature based approach, if we use and we rely on the electrical data, then we have to use some kind of statistical quantifier. So in the beginning, when the technique came into being since the 1990s, the researchers mainly used the statistical measures like root mean square deviation, signature assurance criteria, and so forth. So essentially, it measured the amount of change in the signature, and that they correlated with damage. So this is a non-parametric damage quantification, and it has some limitations. So what our group is doing is that we have suggested, rather than the statistical approach, we are going for mechanical impedance approach. That is, we don't rely on the electrical parameters, but we go deep, we derive the mechanical parameters, and then make our assessment. So there are several models now. The 1D model equation have already shown you, and the equation basically was very simple, which coupled the electrical admittance with the mechanical impedance of the structure. And for 2D also, I have developed a model which takes into account the 2D piezo interactions. So I'm not going into detail, but the final equation which comes into being is this equation. So now here, this ZS effective is a measure of the two-dimensional mechanical impedance of the structure. And what we can now do is, from the measurement we have the electrical admittance, and from this equation we can back calculate the mechanical impedance and use that for damage assessment. Now this is a tricky thing,